Again, welcome to DSRT 734 class, Inferential Statistics in Decision Making. In these lectures, we're going to study about conditional probability and then multiplication rule. So our main objective is to determine conditional probabilities, also distinguish between independent and also dependent events. Use the multiplication rule to find the probability of two events occurring in sequence. Also use the multiplication rule to find conditional probabilities. So first, what is a conditional probabilities? Here we say the probability of an event occurring given that another event has already occurred. So that our condition will be the previous event that occurred. So example would be, what's the probability of A given B? So B has already occurred. So what is the probability of A if B already occurred? And a very simple example would be what the probability of having a lung cancer given that you smoke a cigarette. So again, conditional probability is the probability of an event occurring given some condition. And here we say given that another event has already occurred. So that is our condition. So this is denoted by probability of B given A. So B, again, the vertical line means given. So probability of B given A. So let's start with one example. Again, this is finding the conditional probabilities. So here our question says two cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. So this is a conditional probability. Previously, we studied the classical probability, more or less like finding a proportion of something or relative frequency. But this time we are finding a probability of something given some condition, a previous condition. So our question here says we should find the probability that a second card is a queen, given that the first card is a king, and assuming that the king is not replaced. So we know in our regular decking card, we have 4 kings or 4 queens. So the solution here will be, because the first card is a king and it's not replaced, the remaining deck will have 51 cards. Total, we have 52 cards, and 4 of which are queens. So given probability that B is given A, probability that B given A. Now B will be probability of second card is a queen. But the question said, find the probability that the second card is a queen, given that the first card is a king. So what is the probability that the second card is a queen, given that the first card is a king? Now, the total cards are 52. But since we already having 1 king out, the total card remaining will be 51. But we don't have any queen yet, so we have 4 queens. We have 4 queens, 4 jack, 4 kings, 4 ace. So the answer will be 4 divided by 51. It's not divided by 52 again because we have already taken 1 king, and the total cards are 52. So another second question, finding a conditional probability. Here they say a table shows that the result of a study in which a researcher examined a child's IQ and the presence of a specific gene in the child. Find the probability that the child has a high IQ, given that the child has a gene. So here we can see our high IQ gene present is 33. The normal IQ is 39, gene present. So total will give us 72. So 72 represent the total IQ and normal Q, given that the gene is present. Now, given that the gene is not present, high IQ is 19, normal Q is 11. The total is 30. Now the total for all the IQ, both for gene present and gene not present, is 52. And the same thing, normal IQ, gene present and genes not present will be 39 plus 11, which is 50. And total we have 102 children. So now let's look at our question now. They say the table shows the result of a study in which researchers examine a child's IQ and the presence of a specific gene in the child. Now, find the probability that the child has an IQ. Okay, so this is IQ. IQ. Now, high IQ, given that the child has a gene, so we have to be here. So it will be 33 by 72 because high IQ is 33. And the total children with the gene present, because the condition given is that the child has the gene. The gene present is 72 total. So let's see the solution. So again, we get 33 divided by 72. Not divided by 102 because 102 is the total children, both gene present and gene is not present. But 72 is the total children with gene present. And that was the condition given to us. So the answer will be the probability of B giving A, which is probability of IQ giving gene present is 33. High IQ gene present is 33 divided by the total children with gene present. That's the condition, 72. So the answer will be 0.458. So we have independent and dependent events. So an independent event is an event that does not depend on previous event or previous occurrence. An example of an independent event can be tossing a coin. So if I toss a coin and I get head, that doesn't mean the next one I test, I will get a tail or another head again. I don't know. So it's independent. Dependent event means based on the previous event, we can determine the present event. So let's go through the definition here. Here they say independent events, the occurrence of one of the event does not affect the probability of the occurrence of other events. So the events are independent. So the present event does not determine future event or does not determine what was past event. So it's independent. So the occurrence of one of the event does not affect the probability of the occurrence of other events. So probability of B given A equal to probability of B, or probability of A given B equal to probability of A, because it's independent. So the previous condition or occurrence of any other event does not have any effect on it. So events that are not independent, we call them dependent. So events that are not independent are dependent. So this is what leads us. Dependent events normally lead us to conditional events. So dependent means an event depending on another event or previous event. So here they say we should decide whether the events are independent or dependent. Selecting a king from a standard deck, not replacing it, and then selecting a queen from the deck B. So the solution here is probability of B given A is probability of the second card is a queen, given that the first card is a king, was 4/51. Now, probability of B, this means the event is what? Independent. So we are not relying on A. So probability of B will be 4/52. So we don't care about the king. First card is a king. So the first solution here is dependent. What's the probability that second card is queen, given that the first card is a king? And also probability of B or probability of queen will be 4/52 because we have 4 queens and 52 total card. So here we say dependent, the occurrence of one event, let's say A, changes the probability of the occurrence of another event, second event, let's say B. So we say probability of A giving B, because again, giving B, B can have effect on A. So probability of B, which is independent, probability of queen will be 4/52 because the total queens we have is 4 and the total cards we have is 52. So next, we should find the difference or solving the problem example dependent and dependent events. So now here they say we should decide whether the events are independent or just dependent. So tossing a coin and getting A and then rolling a 6-sided die and obtaining a 6B. So tossing a coin, getting a head, A will be independent. So let's see, it's independent. Probability of B giving A, that is probability of rolling a 6, giving a head on a coin will be 1/6. But probability of rolling a 6 is 1/6. Independent because the occurrence of A does not change the probability of occurrence of B. Because the question says tossing a coin and getting head, which is the event A, and then rolling a 6-sided die and obtaining 6 is event B. So we can see that event B doesn't have any effect on event A, or event A also doesn't have effect on B. So here we say they are independent. The first one will be 1/6 because probability of rolling 6, giving a head on the coin, will be 1/6 because we have 6 sides in a die. And we want to roll 6. So 6 is only 1 by 6-sided. So it will be 1/6. Next, we go to the multiplication rule. So multiplication rule for the probability of A and B. Some textbook use the term intercept. Multiplication rule means when 2 events occur at the same time. So the probability that 2 events A and B will occur in sequence is probability of A and B, which is equal to probability of A times probability of B given A. So for independent events, the rule can be simplified to probability of A and B is equal to probability of A times probability of B. So the first, again, is conditional probabilities. It's dependent. Probability that 2 events A and B will occur in the sequence is probability of A and B equal to probability of A times probability of B given A. But if the events are independent, then we multiply them. So if I toss a coin, what is the probability that the first time I will toss 1, the second time I will toss 2? So it will be probability of getting A times probability of getting 2. So it will be 1/6 times 1/6 because each event is 1/6. So that's the concept here. The first probability of A and B is conditional probability, which will be probability of A times probability of B given A, or probability of B times probability of A given B. And if they are independent, then it will be probability of A multiplied by probability of B. And also this can be extended for any number of independent events. So using the multiplication rule, we have 2 cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then selecting a queen. Now remember, this question said what? 2 cards are selected without replacing the first card. So this selection is selection without replacement from a standard deck. So when we select 1, the total will be 51. Select 2, the total will be 50, etc. So the solution is this. Because the first card is not replaced and the events are dependent, probability of K and Q equal to probability of K times probability of Q given K. Q will be our queens and K will be our kings. The question said 2 cards are selected without replacing the first card, without replacing from a standard deck. Find the probability of selecting a king, then selecting a queen. So we can see probability of selecting a king. How many king we have? 4. So it's 4 over 52. Since we are not replacing, the probability of selecting a queen next time will be 4 over 51 because we have taken 1 out already. So this gives us 16 divided by 2652. Roughly the answer will be 0.006. So again, 2 cards, the example is that 2 cards are selected without replacing the first card. So we are not going to replace it from a standard deck. Find the probability of selecting a king, then selecting a queen. How many kings we have? 4. How many total cards we have? It's 52. So probability of selecting a king will be 4 over 52. Now, what's the probability of selecting a king or a queen given K? A given king. That means 1 card without replacements. So 1 card will be gone. So we get 4 over 51. And the final answer will be 16 over 2652, which is 0.006. So using a multiplication rule, second example, a coin is tossed and a die is rolled. Find the probability of getting a head, then rolling a 6. So getting a head, we have 2 options. When we toss a coin, we have head or tail. Rolling a die to get 6, we have 6 different options. So the probability for rolling a coin to get 6 will be 1/6. Probability of getting a head will be 1/2 because head is 1, tail is 1, so 50%. Let's see the solution. So here we say that since the outcome of the coin does not affect the probability of rolling a 6 on a die, the 2 events are again independent. But probability of H, which is getting a head, and also getting the die, when I roll the die, getting 6 side. Head means tossing a coin, head or tail. So you can see probability of H is half, 50-50. But the next one is times 1/6. Because rolling a die, we have 6 sides. So if I want number 6 to come or 3 to come, then it will be 1 value over the total possible values in the die, which is 6. So here the answer will give us 0.083. Next question, they say using the multiplication rule again, the probability that a particular nail surgery successfully is 0.85. Find the probability that the 3 nail surgeries are successfully. So probability that a particular nail surgery is successful is 50.85, 85%. Find the probability that the 3 nail surgeries are successful. So here we have 3 surgeries are successful. The probability of their success is 0.85. So we have 0.85 times 0.85 times 0.85. But we have 3 materials. And that gives us 0.614. Then next, we find the probability that none of the 3 nail surgeries is successfully. So because probability of success for 1 surgery is 0.85, the probability of failure for 1 surgery will be 1 minus 0.85, which will give us 0.15. Now, probability of none of the 3 surgeries is successful. then we have 3 failures. So to be 0.15 times 0.15 times 0.15, which will give us 0.003. So the question again said we should find the probability that none of the 3 knee surgeries is successful. And when we go back once, we'll see that let's go back. Yeah, this is the question. The probability that a particular knee surgery is successful is 0.85. So find the probability that the 3 knee surgeries are successful. Probability of success is 0.85, and we have 3 of them. So we get 0.85 times 0.85 times 0.85, which will give us 0.615. This is independent event because the first surgery, if we succeed, that doesn't mean second we are going to succeed or fail. So it doesn't depend. It's independent. This is one of the tricks in probability. Most probability questions, we know the formula already, but there are so many formulas based on the conditions. So we have to understand the problem, the condition of the problem, then apply the right formula for the problem. So here they say we should find the probability that none of the 3 knee surgeries is successful. None of them. The success is 0.85. So not successful will be 0.15. And since it's 3 surgeries, we multiply 0.15, 0.15, 0.15. And that's give us 0.003. So find the probability that at least one of the knee surgeries is successful. So at least this is we'll say cumulative probabilities. We can get at most 1 means we can go at least up to 1. At least 1 means we have to start from 1. And remember the highest is 3. So at least means 1 or more. At least means 1 or more. The complement to the event at least 1 successful is the event that none are successful using the complementary or complement rule. So probability that at least 1 is successful will be 1 minus P, which is none are successful, which is 1 minus 0.003, and our answer will be 0.997. So let's see another example here, using the multiplication rule to find probabilities. Here they say more than 15,000 US medical school seniors applied to residence programs in 2007. 15,000 US medical students, seniors. Of those, 93% were matched to a residence position, 93 of them. 74% of the seniors matched to the residency position were matched again to one of their top 2 choices. Medical students electronically rank the residence programs in their order of preferences, and program directors across the United States do the same. The term match refers to the process where a student's preferences list and a program director's preferences list overlap, resulting in a placement of a student for residence position. So first thing we do, we find the probability that a random selected seniors was matched a residence position and it was one of the seniors' top 2 choice. Find the probability that the randomly selected senior was matched a resident position and it is one of the seniors' top 2 choice. So solution means match to residence position A, B matched to one of the 2 top choices. So probability of A is 0.93, probability of B given A will be 0.74, and probability of A and B will be probability of A times probability of B given A, which will give us 0.93, which is probability of A times 0.74, which is probability of B given A. B given A. So next, find the probability that a randomly selected senior that was matched to a residence position did not get matched with one of the top senior senior top two choices. So here we use the complement first. Probability of B complement given A will be 1 minus probability of B given A. And we know probability of B given A is given to be 74% or 0.74. So we get 1 minus 0.74. So this will be the summary of our topic. In this topic, we focus on conditional probabilities. Again, very important. And it reads like probability of A given B. So A vertical line, B. The vertical line means given. So that's the condition. We also distinguish between independent and dependent variable. Independent variable means none of the variable depend on each other, whether the previous one or the future one, or based on any condition. Dependent event means, again, there is a condition. So we can apply probability of A given B using dependent events. Independent event, no. Use multiplication rule to find probability. If the events are independent, then the multiplication will say probability of A times probability of B times probability of C. We also use the multiplication rule to find conditional probabilities. For example, probability of A and B is probability of A times probability of B given A. Again, if they are follow the multiplication rules and also the conditional probability. So we're going to end somewhere here and then wish everybody the best. Again, if you have a question about the lectures, you can send an email. Again, this is DSRT734 and our topic was conditional probabilities.